Hello everyone, it's me Gagan Kumar present over here to teach you physics. Let's move on to the video. Today we'll discuss electromagnetic induction. In this chapter actually already we have completed in the last two lectures about Faraday experiment and Lenz's law. Now today we'll discuss motional electromotive force. So this part will focus today. So motional electromotive force and energy conservation. And here in the last two lectures we have completed already what is Lenz's law, what is Faraday's law, and what is the experiment of Faraday and Henry, their observation and conclusion. Okay. So if we will talk about this, so here basic idea is if there is a relative motion between one coil and a magnet, then what will happen? Now there will be induced EMF or induced current will be produced in the coil. So this is the basic idea was there. Now we will try to solve some multiple choice questions based on this. So whatever we completed already in lecture 1 and lecture 2. So let's move on to that. So you understand here some multiple choice questions are here, and this all questions PPT format you will get in our description box. So you check our description box, their link will be given for this all PPT. So what you do, so you can download and you can have this MCQ question with you, okay, if you want, with the answers. So now try to understand the question number 1. So here what it is given, it is given when a magnet, this is the north south, a magnet is there. When this magnet is pushed in and out, when a magnet is pushed in and out of a circular coil, so here one circular coil is there. So actually this coil is looking not that much circular, so you can understand like this type of circular coil. So here some connection is there, okay. So this is in and out on to a circular coil, and it is connected to a galvanometer as shown in the figure with a frequency nu. So that means this magnet is brought with a frequency nu. So what you basically in and out means actually a coil is like this is the magnet, you are taking out and taking in like that, in out like that. So if you are doing like this something, so there will be some frequency of this pen or of this magnet. So if a coil is there, if a magnet is like this, some frequency of magnet is there, that is basically saying nu. Now they are telling which of the following options are correct. Okay. So now first thing is constant deflection is observed in the galvanometer, and second option is telling visible small oscillations will be observed in the galvanometer if frequency is about 50 Hz, and they are telling oscillations in the deflection will be observed if a frequency is 1 or 2 Hz, and no variation in the deflection if frequency is 1 or 2 Hz. So like these 4 options are given. So listen, whenever you are taking a magnet in and out, we understood that here what will happen, the induced EMF or induced current will produce in the coil. And remember that magnet frequency should be less to observe the deflection in the galvanometer. Okay, if a frequency is more, you cannot observe the galvanometer deflection. So here you check where the frequency is less. So here frequency is 1 Hz, 2 Hz saying. So this will be your correct answer. Your galvanometer deflection will happen when frequency is less. Frequency of what? Frequency of this magnet. Okay. So coming in, going out like that. So always remember, in a coil, if there is a more frequency for this magnet, there will be, you cannot observe any deflection. If less only you can observe. So according to that, your answer is C. Answer is C. I hope you understand this. Now come to the next question. So you can write it, or if you are not writing also, you can download the PPT format from the description box. One link is given already. Okay. Now see MCQ 2. Now here one diagram is given. So actually here two coils are there, A and B, and the coil A is connected with switch K, and coil B is connected with a galvanometer G, and also coil A is connected with an AC source. So here one AC source is there, alternating current source is there. Now that link same thing. So what will happen if a key is closed? If key is closed, what will happen? So try to understand, similar options are given how we did the previous question. So when frequency is less means when 1 to 2 Hz frequency for this AC source, then what will happen? There will be some oscillations in the galvanometer. So option C again. Okay. So previous case you are taking in and taking out that magnet, but in this case it is different little. One AC source is connected. So actually when key you press, so here a current will be there. Due to current, some flux changes will be there in the other coil, and there will be some induced EMF or induced current. Due to that one, some deflection will happen here. Okay. And this AC source, whatever you are giving here, that frequency should be less. So here they asked about AC source frequency, but in the previous case they asked about magnet frequency. I hope you understand. Okay. Now next question, see, an induced EMF is generated when a magnet is withdrawn from the solenoid. This one your Faraday's experiment, already you know this. Either you take out or you take in. Okay, either take out or take in from the solenoid a magnet. Definitely there will induced EMF will generate. That means this assertion is correct. So it is assertion region type question. So assertion is correct. And in region you see the relative motion between magnet and solenoid induces EMF. So this is also correct. Actually when there is a motion between a magnet and solenoid, there will be induced EMF. So here assertion also correct and region also correct. Okay. Now what you have to find here? Now here you have to find, if you both are correct, assertion and region, is this region is correct explanation for assertion? I will see that is correct actually, because I told if there is a relative motion between a magnet and a coil, there will be induced EMF. So whatever it is happening here, that is due to relative motion. So this both are related and correct explanation. So answer will be here option A. Okay, so try to understand assertion region question. If there is a relative motion between magnet and solenoid, EMF will induce. Okay. I hope audio is clear. If anyone have doubt, you can chat. You can ask. Okay. Now come to the next question. In electromagnetic induction, the induced EMF in a coil is independent of what? Option A, change in flux. Option B, time. Option C, resistance of the circuit. Option D, none of the above. So you try to give answer. Those who are watching, please you give to answer. What can be answer? In electromagnetic induction, the induced EMF in a coil is independent of what? See, when induced EMF formula you check, induced EMF formula is, okay, E, or like this also E you can write. Okay, so that is your minus d phi by dt. If there are n number of terms also there, you can take n. Okay. Now here change in flux is there, so it basically depends on change in flux. here time is there, so here in EMF also time is there actually, so it depends on time. But in this case I am not getting anywhere resistance, so that's why your answer will be what? Now induced EMF is independent of resistance of the circuit. Okay. So remember, induced EMF does not depend on the resistance, it depends on the change in flux, depends on the time, okay, or rate of change of flux. Okay, I hope you understand. Now next question you try to give answer. In electromagnetic induction, the induced charge in a coil is independent of what? The previous question is induced EMF. Now here you see this is induced charge. So already in the last lecture I have told induced charge, Q induced, it is called basically induced charge. So what is the induced charge formula? The induced charge formula is change in flux by resistance. Okay, change in flux by resistance, like this one I have already given, or final flux final minus flux initial by R. So R is the resistance of the circuit. That means induced charge depends on change in flux and resistance of the circuit. It does not depend on time. So this will be correct answer in this question. Induced charge in a coil is independent of time. Okay. Now come to this question. Here the magnetic flux linked with a coil is given by an equation. So phi equal to 8t square plus 3t plus 5. So what is given here? Now magnetic flux. So 8t square plus 3t plus 5. The induced EMF in the coil at the 4th second. So what do you mean by 4th second? Now t equal to 4. 4th second means t equal to 4. So here some options are given. Try to understand. If your magnetic flux is 8t square plus 3t plus 5, how to find induced EMF? So remember the formula? Already in the last two lectures we have discussed. Lecture 1 we have discussed already. What is induced EMF in terms of flux? That is minus d phi b by dt. Now d by dt is called basically derivative with respect to t. So to do differentiation or derivative of this magnetic flux with respect to t, it is minus d by dt. Phi b is 8 t square plus 3t plus 5. Okay. But remember here they have not given any minus sign here. That means they have calculated in terms of magnitude. So let me calculate. After that magnitude I can take, I can give the answer. Now here see differentiation. If I will do this term, how to differentiate this? Now here each term you differentiate. D by dt of 8t square plus again d by dt of 3t plus d by dt of 5. D by dt of 5. Now try to understand 8t square derivative. What is 8t square derivative? Now remember 8t square derivative is what? Now 8 is a constant, it will come out, and t square derivative is 2t. How it is coming t square derivative 2t? Now remember d by dt of t to the power n equal to n into t to the power n minus 1. You know this formula for derivative? Okay. For all values of n it is valid. Now 8 into 2t plus similarly 3 is a constant will come out and t is the variable. So dt by dt will get 1. dt by dt will get 1. and here only one constant is there, that is 5, and you know constant derivative is 0, so here I will put 0. The constant derivative is 0, so I will put there 0. Now you can keep minus here, you can keep minus here. Now next listen. So what is my EMF here? Now my EMF is minus 16t plus 3. So what is coming here? You can calculate also now, minus 16t plus 3. But they asked t equal to 4 seconds, you say what is EMF. So now you can substitute the value of t here. Now substitute the value of t. Now here EMF equal to minus 16 into 4 plus 3 minus 64 plus 3, that is coming minus 67. So my EMF is coming minus 67, but here minus is not given, that means they have taken in terms of magnitude. Okay, and if flux is given in Weber, so that definitely this will come in volt, because EMF SI unit is volt. Induced EMF also SI unit is volt. Okay, potential difference, induced EMF same thing only, unit. Now minus is not given, so that means I can understand here they have taken in magnitude format. So it I will write it as plus 67 volt. Okay, so answer will be option C. So you can calculate also yourself, simple derivative. Okay. Listen, suppose in this question there are two options, one is minus 67 volt and one is plus 67 volt. Two options are there, and they only mentioned induced EMF. Then which option you have to choose? Now more correct will be this one, because in our induced EMF there is a minus sign is there. Okay. So but when we take magnitude, it will become minus, will become plus. Okay. So if sometimes they can mention suppose magnitude of induced EMF, if magnitude of induced EMF they mention, then minus no need to take, you take plus. Okay. So I hope you understand. So the next question will be similar type. You try to solve. The magnetic flux linked with a coil is given by an equation 3t square plus 40 plus 9. 3t square plus 40 plus 9. The induced EMF in the coil at 2 seconds. That means here time is given 2 seconds. Similar model question, please you try. So what is flux is given? 3t square plus 4t plus 9. Now if I want to find EMF or induced EMF, so what I will do now, minus d phi by dt, or if a magnetic flux B I am saying here, so phi B I can take. Now calculate here. Now minus d by dt of 3t square plus 4t plus 9. Okay. If you know the formula correctly for derivative, then directly also you can do. So I can do here directly. So minus t square derivative is 2t, 3 is there, so it is 6t, plus 4t derivative is 4 and a 9 derivative is 0. So my EMF is coming minus 6, minus bracket is there 60 plus 4. Okay. Now next listen. Now here EMF equal to minus 6 into 2, because they are asked at t equal to 2. So my EMF at t equal to 2 second. Plus 4, now you calculate this one, minus 12 plus 4, so it will be minus 16 volt. But remember here minus is not there, that means they are given in terms of magnitude. So that means you can take your EMF magnitude is nothing but, that is minus 16 volt magnitude, which is plus 16. Okay, so your answer will be D. Answer will be D. So it is easy, only you can calculate. Those who are watching, please try to solve yourself and you can send answer in the live chat. Okay. Now see the next question. Those who are writing slowly, please you pause the video and you write. Okay. Now if a copper ring is moved quickly towards south pole of a powerful stationary bar magnet, then what will happen? Now see, a magnet is there, north south suppose. Now a coil is there here, one coil is there. Now coil is suddenly moved. If coil is suddenly moved, what will happen? There will be some flux change in the coil. Okay, because the relative motion is happening between magnet and coil. Although magnet is stationary, but coil is moving towards magnet. So that's why there is a relative motion. So there definitely one induced current will produce in the coil. So current flows through the copper ring. Okay, so your answer will be A. So very simple question, try to understand. Okay, so the answer will be A. Now come to the next question. Magnetic flux in a circuit containing a coil of resistance 2 ohm changes from 2 Weber to 10 Weber in 0.2 second. Now the charge passed for the coil in this time is what? The charge means that is induced charge. So definitely you have to go for induced charge. So what is the induced charge here? A change in flux by resistance. So you know already induced charge formula is change in flux by resistance, and you can tell also final flux minus initial flux by R, like that also you can give. Okay, but you see here no time is coming, no time term is there, so this one no need to take, no need to consider. Now what is the final flux? Now 10 Weber, so final flux is 10 minus initial flux is 2 given here, divided by resistance is 2 ohm, this is your R resistance, that is your 2. So it is 8 by 2, which is basically 4. So 4 coulomb. So answer will be D. Answer will be D. So simple formula. If you induced charge formula you remember, then directly you can do this question. Okay. Now come to the next question. So induced EMF in a conducting loop of wire will be non-zero when it rotates in a uniform magnetic field. Okay, that means they are telling a conducting loop is there and it is rotating in a uniform magnetic field. Okay, so there will be one induced EMF will be there. It is actually correct statement. So if there is a flux change, then definitely there will be induced EMF. Now they are telling the EMF is induced due to change in magnetic flux. Yes, that is also statement is correct. That means here A and R both are correct. Both are correct statement. Now next is what? Is this correct explanation? Yes. It is correct explanation because due to change in magnetic flux only induced EMF is created. And remember that the conducting loop is what doing basically? Now it is rotating. And remember that rotation should be, how you know? Magnetic field is like this, rotation should not be like this, rotation should be like this way. So that flux changes should happen. So this is the correct statement you can tell, and answer will be A. Okay, answer will be A. Both are correct and R is the correct explanation of our session. Now come to next question. A coil of area 100 centimeter square. So area is given how much? Area is given 100 centimeter square. Magnetic field of 0.1 Weber per meter square. So B is given 0.1 Weber by meter square. Is perpendicular to the coil. That means coil and magnetic field. It is like this type of things. Coil, this one is the coil. This is the magnetic field. Magnetic field is perpendicular to the coil. This is your area vector A. Because area vector is always perpendicular to the surface. So B and A both are in the same direction. Definitely there will be some flux. Now the field is reduced to 0. So that means if it is initial field, now final field is what? Now it is reduced to 0 in 0.1 second. That means T is given 0.1 second. T is given 0.1 second. Now what is the induced EMF in the coil? Now the same formula, EMF is minus d phi by dt. Okay, and if number of turns is there, you can put n. So here it is given n number of turns, so n equal to 500. Now next listen. Now here EMF minus n d phi you can write as b into a, but basically here change in flux is happening for what? Now change in flux is happening for magnetic field. So I can write here like this. Final magnetic field minus initial magnetic field into A. Now next it is a circular coil, area is given already, and you will remember here D is given in SI unit and area is given in centimeter square, so definitely there is changes needed in unit. That one I will do here. So it is 500 into B final, I can tell 0 minus B initial, that is 0.1 into area. So what is area? 100 centimeter square. I can write 100 into 10 to the power minus 4, because you know 1 centimeter 10 to the power minus 2 meter and 1 centimeter square is 10 to the power minus 4 meter square. So I converted centimeter square to meter square. Okay. Now next see. Now here EMF divided by time. Time is given 0.1. Time is 0.1. Now this minus 0 minus 0.1. So it is minus 0.1. So minus minus will become plus. Now here it is 5 into 10 to the power 4 into 10 to the power minus 4. Okay. And into 0.1 divided by 0.1, because this 20 will become 10 to the power plus 4. Okay. So now you can cancel and you can get the answer. Now here this will get cancelled and 0.1 will get cancelled. So answer is 5 volt. So EMF is coming how much? 5 volt. So check, answer is option B. Answer is option B. Okay. Now come to the next question. The variation of induced EMF with time in a coil of short bar magnet is moved along its axis with a constant velocity is best represented as what? Now one magnet is there and one coil is there. So see here magnet, north south magnet is there, and here this is the coil. Now here they are telling induced EMF is producing in the coil when a magnet is passing through the solenoid. Actually it is solenoid actually. Now what they want here? Now what is the graph of induced EMF and T? What is the graph of induced EMF and T? Now listen, in the graph you will see normally this A, C, D options are given positive, like everything in positive actually. But in B there is some negative and some positive, like that it is given. So actually what will happen whenever this magnet will come inside the solenoid, there is a increase in flux. Okay. So that time induced EMF will produce in such a way that it will try to oppose that and one direction will be there. Induced EMF or induced current direction will be there. But when it will come out, that time flux will decrease. And induced EMF will produce in such that it will try to increase the flux, or it will try to attract the magnet. So that time in a different direction it will form. So definitely there will be two opposite direction of induced EMF. That means that will be one positive, one negative, like that. So only this in the B graph there is the directions are given. Okay. So negative, positive, like that. If you want to check that, you can check here. EMF equal to minus d phi by dt. Now remember, when it is going inside, there is an increase in flux, so delta phi is positive, so EMF will be definitely negative, because d phi will be positive. Okay, when it is going inside. So that's why in the first case your EMF should come negative. Next EMF will become positive when d phi is negative. So why d phi negative? Because when it will go out of the coil, this bar magnet, that time flux will decrease. So change in flux will be negative. So in that point you can understand, and here it will be plus. So this answer will be correct, B. One polarity changes will happen in the induced EMF. Polarity changes, that's a minus plus, both graphs will be there. Okay. So I hope you understand. So lecture 1 MCQ completed. Now the second part, lecture 2, that's Lenz's law and all, that MCQ will complete. After that we'll move to electromotive force. Okay. Now listen, all this MCQ PPT will be given in the description box, so you can click the link and you can get the PPT. Okay. Now come to here. So in the Lenz's law, some questions are here. Lecture 2 MCQs. A copper ring is held horizontally and a bar magnet is dropped from the ring with its length along the axis of the ring. Then acceleration of the falling magnet will be what? So what exactly they are saying here? They are saying here a coil is there. In this coil, one bar magnet is falling. Okay, one coil is there, horizontally it is held coil. One bar magnet is falling. Suppose this is the north pole, this is the south pole. It is falling down like this. Okay. Now what will happen? Now when it is coming towards this coil will try to oppose this magnet. So it will try to create a north pole like this one. Already explained in the Lenz's law. So it will try to create a current like this anti-clockwise. If you will see from the top, anti-clockwise current will be there. So it will try to behave like a magnet, and its north pole will be upward. It will oppose that magnet, the magnet which is falling. Next, here if it north pole will be there together, then repulsion will happen. So this will get one upward force. So I can write here. So this is the north, this is the south. It's moving with acceleration A, and mg is downward because this will have some mass. Magnet will have some mass, and one repulsive force due to induced current. It is developing one north pole here. Okay, that one I can show in dotted line actually. In dotted line I can show here. Okay, so here one north pole, here one south pole. It is behaving like a magnet. You know, circular current carrying coil can act like a bar magnet. So when induced current is producing, it is behaving like a magnet. That north pole repulsion is happening. Due to that, one force is upward direction for this magnet. I will apply Newton's laws of motion. This magnet is falling downward with acceleration A. So what I to find? I will find like this: mg minus f equal to ma, because mg will be greater as it is falling down. Now from here, if I want to find acceleration A, it will be g minus f by m. M is the mass of the magnet. M is mass of the magnet. Now see here, your acceleration is coming g minus f by m. That means this is the acceleration of the magnet. So the acceleration of the magnet is little reducing as compared to g, and the term is whatever reducing factor, it is f by m. So definitely what is answer here? Now the acceleration of the falling magnet is less than g. Okay, acceleration of the falling magnet is less than g. I hope you understand. So this is the free body diagram of the magnet I did, and then after we are calculating acceleration. Now next come to here. MCQ 2. A metallic ring is attached to the wall of a room. When the north pole of a magnet is brought near to it, the induced current in the ring will be what? Now this is the coil, this is the magnet. Magnet is falling. Then what is the induced current in this coil? So in this coil, what is the induced current? So what to do here? The same thing actually in the previous case. You see, if a magnet is coming, this off side will act like a north pole. Now here current will produce in this way. So this current, if from the top you will see, it is anti-clockwise direction. It is anti-clockwise direction it will show. Okay. So that's why the answer will be anti-clockwise direction. If south pole is coming, suppose instead of this north here, here south should be there, then it will behave like south, and here from up you will see it will look like clockwise direction. But in this question particularly they have given what is it is now north pole is coming. So north pole is coming means this magnet will, this coil will behave like a magnet, north pole will be upward direction. So you draw a north here, N you draw, then after give arrow like this, then you can give arrow in this coil itself. Okay, N like this, N you do, okay, like this one you can do, then the coil is there, then you can give the directions like this. Okay, so anti-clockwise direction. The next lesson, Lenz's law gives the magnitude of the induced EMF, never. The direction of induced EMF, this is correct actually. Last class I told Lenz's law gives the direction of induced current. Okay, direction of induced current, how it is clockwise or anti-clockwise in a coil, it gives that. So both magnitude and direction won't be, and the magnitude of the induced current it won't be. Okay, so B answer. Now MCQ 4. In the diagram, if a bar magnet is moved along the common axis of a two singleton coils A and B in the direction of arrow, so two coils are there A and B. Now north south one magnet is there, north is left side, south is right side. Okay, so if this picture is not visible, you can increase the quality of your video in the YouTube settings. You can go, you can give for a high quality picture. Okay, now listen. So how current will produce here? Here if it is going, this north pole is going from this coil A, it will behave like south. So here current will be this way, current will be this way. Okay, it will try to attract the magnet because it will oppose always the cause, already discussed in Lenz's law. Now in the B, what will happen? In the B, if south is coming towards this coil, then it will try to repel. It will try to repel, and you understand this is up, this is down, this is the down side, this is the up side, like that one you assume. Now it gives south like this. Now here it is south is like this coming. Okay, so now what is happening? You just imagine this is actually your what? This is your up side, that is your down side. This is your up side because you are watching from here. From this side watching, from south side you are watching, this is your up coil, because coil is there means this is your up side like this is your down side. Now what will happen is, see here also up, here up. See, both are in opposite directions. It is going up, it is going down, so arrows. Okay, so that means what is happening when, remember when two coils are there, a magnet is just passed, then in the both the coils induced current will be there, but that will be in opposite direction. That will be in opposite direction. Try to understand. Okay, this Lenz's law looks a little difficult to identify the induced current direction. Okay, so be careful, just understand when south pole is coming it will behave like south, when north pole is going it will behave like south. This coil will behave like south because it will try to attract the magnet, but when south is coming it will try to repel because flux is increasing, it will try to decrease the flux. But when north pole is going out, flux will decrease, but this coil will try to increase the flux, that's why it will attract. If magnet comes only, flux will be more. Okay, so that statements you remember in mind. I hope you understand. So your answer will be induced current in A and B are in opposite direction. Now come to next question. A magnet is dropped down in an infinitely long vertical copper tube. So then what will happen here? So listen here what I will tell. Now if a vertical copper tube is there, and a magnet is dropped here, the north to south magnet suppose it dropped, just you are making it fall. Then what will happen? This magnet will move with certain speed, it will move first, but when it will go, there will be some flux change inside this coil, inside this tube. Due to that one, some induced EMF will produce or induced current will produce in the coil, and that will try to oppose the falling, because due to magnet falling, current is inducing. So now that induced current will try to oppose this when it is inside, and what will happen after some time, you will see that, okay, here one force is acting, repulsive force, and here it is mg, So they both will balance and it will move with a constant speed. They both will balance, it will go with zero acceleration or with constant speed. So that will happen. So this hollow cylindrical tube is a copper tube, okay, and NS is basically a magnet. So you understand this and put your answer is A. The magnet moves with continuously increasing velocity. It will go with certain speed, it will go with high speed, but after some time what will happen? It will acquire a constant terminal velocity. That means a constant velocity, okay. But initially when it will fall, it will go with certain speed. In the middle or here somewhere, its speed will become constant, okay. I hope you understand. Answer will be A. Now MCQ 6 you check. Lenz law violates the principle of conservation of energy. Actually this assertion is wrong. Okay, why wrong? Because Lenz law supports the principle of conservation of energy. That means Lenz law is in accordance with the principle of conservation of energy. Reason: the induced EMF does not oppose the change in magnetic flux responsible for its cause. Actually induced EMF opposes the cause, but here they are telling does not oppose. That means assertion also wrong. So both are wrong here. So right here assertion and reason both are false. So both are false here. Okay. So you can write this MCQ number and answers. Later you can copy in your note if you are not able to write. Otherwise you can pause the video, you can write the MCQ. Okay. But try to understand the concept, that is important here. Now see, a rectangular loop and a circular loop are moving out of a uniform magnetic field. To a field region, a field free region. That means here one magnetic field is there. You can see the cross. This is the magnetic field, actually cross magnetic field, that is inward magnetic field. Magnetic field is pointing inward. Now here there is no magnetic field, so it is coming out of the magnetic field. In which loop do you expect the induced EMF to become constant during the passage out of the field? Okay. So now listen. Here magnetic field is like this. Your magnetic field is like this. Cross magnetic field means inward magnetic field. Okay. Now when a rectangular loop will come out, its area will come out. That area with respect to time will not change. So dA by dt, area change with respect to time will be constant. Okay, because this shape is only coming out. This because the side will be always constant here see. Okay, between a rectangle, you know, this distance is always constant. But here what will happen? Now when this will come out, when it will come out, the loop will be like this, little like this. Okay, try to understand when this will come. So here this much area is coming out only. Then when it will be little, what is happening? See here, area changes happening with respect to time. So when it will come little more, half of the circle, then this much area will come out. So with respect to t, its area is increasing. Okay, so you can write here what? Now dA by dt for this type of loop is what happening? Now dA by dt is not constant. dA by dt is not constant. So that means definitely what will happen if dA by dt is constant in EMF you get what? Minus n d phi by dt. Otherwise if a magnetic field is constant you can get dA by dt. Okay. So that means if dA by dt is constant, then here what will happen? EMF also remains constant. So that in this coil, in the rectangular coil, okay. So what will happen? Now area change is constant, so EMF also constant. If area change constant, then EMF also constant. But in the circular loop or elliptical loop, area change is not constant. So what will happen? Now EMF also not constant, because at the time passes when it will go out, its area will change. Okay, area will change means some small area will come out, then again large area will come out. Difference, what will happen now? With respect to time, this area if you check, you see this area, shaded areas,
that will change. Okay. So you can understand this. So rectangle loop will have constant EMF during the passage out of the field region. Okay. So rectangle things you just understand. I hope you got the point. Now next move to electromotive force. Okay, so what is that one? We'll see. Motional electromotive force, induced EMF due to a moving conductor. That one will go. Okay, so we'll understand what is motional electromotive force. Then after we'll go some energy like power, current calculation will go. Okay, so try to understand this. Okay. So motional electromotive force. Actually, what is this one? Now here you have a magnetic field. Just first try to understand, then after we'll do the derivation and all. You have a magnetic field. In this magnetic field, what is happening? Now a conductor is there. This PQ is a conductor. This PQ a conductor. P here, Q here, point. Now this is moving with certain speed V. Moving certain speed V or velocity V. Now if it will move in this magnetic field here, then what will happen? This conductor will behave like a battery. Why? Now in this conductor EMF will induce. Okay, in this conductor what will induce? EMF will induce. So it will become like a battery, and if you will complete a circuit like this, then what will happen? Now current will flow in this circuit. Current will flow. That means previously we are changing the magnetic flux and we are getting the induced EMF, but now we are not doing that. In this we are moving a conductor. Either you can move this way also, you can move that way also. You are moving a conductor and you are getting what? EMF. Electromotive force means EMF, right? So basically what you are getting? A motional EMF you are getting. Motional EMF. So due to motion of conductor you are getting EMF. Or you can tell a running conductor. This conductor is when running, when moving in a constant uniform magnetic field, a running conductor is behaving like a cell or battery, like that you can say. Okay. So for this one, first we will discuss some derivation thing, small derivation only. First you need to do this picture. So everyone you can do the picture, you can pause the video, you can do, otherwise you can do also now. Now in this picture what you have? Now we have a cross magnetic field. This cross whatever you are seeing, this is a magnetic field B given, cross magnetic field, and PQ is a conductor and its length also given. How much length? Small l. So small l is the length of the conductor. And one circuit is connected here like this, conducting circuit is connected, and in that circuit if you can take also, you can take the resistance. Basically resistance is R. We will consider later. So first you consider this one. Okay, consider a conductor and length L, P, Q, R, S, some points you write, and from this end to this end distance is x. You can take speed of the or velocity of this conductor is basically V you can give. So picture perfectly you can do, and here little language you can write for derivation purpose. I am telling this one. Let us consider a straight conductor PQ is moved towards the left with a constant velocity V in uniform and time independent magnetic field as shown in the figure. So these things you can do for this. Okay. And already I explained you what we are exactly going to do here. Now exactly we want to see that if this running conductor is becoming cell, then what is the EMF? So what is that EMF will calculate. So that is our main idea. Okay, if a running conductor is becoming cell or it is behaving like a cell, then what is the EMF? And what is the current also in this circuit? So that also will try to find it out. Okay. So I hope you understand the idea. So do the picture. So this cross is B magnetic field, L is length, PQ is length of this rod, okay, and X is the distance. Here you can check, and all points you give properly and write this language also. Now listen, if the length RQ equal to X, so that this is the length RQ equal to X, so this is the length R and Q, this length is X, and RS equal to L, so this one is your L, length RS. Now the magnetic flux phi B enclosed by the loop PQRS will be how much? Now phi B will be BLX, because you know, see this one, here it is PQRS, this is a loop actually, inside some magnetic field is there, and if you want flux you want to find, what is that flux? Now magnetic field into area, magnetic field into area. Now magnetic field is how much? Now magnetic field is B, area is how much? Now length is L, breadth is X, so area is L into X. So magnetic flux is how much coming? Now BLX. Okay. So in this area PQRS, what is your magnetic flux? Now that is BLX. So that is what we are saying here. That is what we are saying here. Here RQ is X, RS is L, the magnetic flux is BLX, and where X is changing with the time. Why X is changing with the time? Because when this rod will come towards left side, then what will happen? This X changes, distance X changes, so it depends on the time. According to time, X is decreasing. Okay. Now the rate of change of flux phi B will induce an EMF. So as X is changing, flux also will change. If X is changing with the time, flux also will change with the time. That flux change will give you EMF. That EMF let E. That EMF let E. So this EMF is nothing but it is minus d phi B by dt. So phi B means magnetic flux. Now what you do here? Minus d by dt. So phi B is nothing but what it is? BLX. So now put here BLX. Now minus B and L are constant. B is a uniform magnetic field and L is length. So constant length, so you can take out and you can do here dx by dt. And here what I will take? Now minus BL, this is dx by dt I will take as a V, but I will take as a minus V. Let me take as a minus V. Why minus V? Now because X is decreasing with respect to time. So the decrement is given minus V. Suppose it is going towards right. If this is going towards right, then dx by dt is increasing. So in that point you can take that is what? X is increasing with the time, so you can take positive, but here you take as it is decreasing, you take minus. So minus B. Now here if I take my induced EMF, how much it is coming? Minus minus plus, so it is BLV. So this is my motional EMF. This is my motional EMF. Okay. So we are running conductor is behaving like a cell, and that if it is behaving like a cell, then it will have certain EMF. That EMF is nothing but it is BLV. B is magnetic field, L is length, and V is the speed at which it is moving. Okay. So this is what you have to understand here. EMF. Now after finding EMF, now we can go for induced current. Okay, so these are basically induced EMF also, you can tell motional induced EMF. Now you can find the current flowing through the circuit. After current also you can find what is the force acting on the conductor, what is the power, everything you can find it out. Okay. So please note it down. I hope you understand. Okay. Now next listen here. The same derivation BLV we can find in alternative method also. That one I will say you later. Now motional EMF you keep in mind. Now suppose you are saying this conductor is behaving like a cell. So that means this conductor will behave like cell means in cell you know there will be some positive terminal and some negative terminal. It will be like this, right? Some positive terminal, some negative terminal. Okay. Now this conductor will behave here certain things like this. Then how to identify which is positive terminal, which is negative terminal? Now to do that, you find V cross B. What do you find? You find V cross B. V cross B. So V cross B will give you positive terminal of cell. Terminal of cell. How it is coming, that one we will discuss also. So first you find what is V cross B. See, V is left direction. So V is left direction, and magnetic field is where? Magnetic field is cross direction. So V is like this way. The magnetic field is cross. Okay. Now if you do V cross B, you see if you do V cross B, you will get that V cross B direction. So V cross B, if you do, this thumb will give. Cross product, you know, thumb will give the direction of V cross B, it will be downward actually. So here Q will become positive terminal. This Q will become what? Q will become positive terminal. Q will become positive. And P will become negative terminal. The P side will become negative, higher, lower potential, and Q side will become positive terminal. That means how it will be? Now here things will be like this. Here things will be like this. This is your circuit. Now this battery will become like this, your conductor. Okay, so this will become your negative, this is your positive. So big terminal is positive. Now this is your P, this is your Q. So now this is your EMF, this EMF value is BLV. This EMF value is BLV. Okay, so you know this bigger terminal is positive terminal and smaller terminal is negative terminal. Okay, so V cross B will give you positive terminal of the cell. So V cross B you do, it will be pointing downward. Okay, because in this direction is B, in this direction is what? V. If you V cross B will do, so downward will look, thumb will give downward direction, so that is your positive terminal. Okay. Now here we will write that one. So what will write? Now suppose we have a circuit, in that circuit we have this one. One resistance is R and this conductor is moving. So this moving conductor is behaving like a cell, and this terminal also we are giving here, terminal we are giving negative, this is positive. Okay, like this we are giving the same thing actually, or you can write also here sometimes, you can write what? Now the terminal P has higher potential. The terminal, sorry, we check here, what is this? Terminal Q. Terminal Q is at higher potential. Terminal Q is positive, and terminal Q is, and the terminal Q is, terminal P is negative. So positive means higher potential and negative is lower potential. Okay, that one you can give. The same thing we are doing here. So this is your P, negative terminal, this is your Q, positive terminal. In this direction if you see the current, you know, okay. So P is negative terminal, Q is positive terminal. Now current will come out of the positive terminal, that one we know. For a cell, current will come out of the positive terminal and will enter to the negative terminal. That means this is the direction of current we are giving. This is the direction of current. So for more visibility I am giving with red also, red pen. So now see here. Okay, this is the current. Now this is the current here I. Now if I want to find this I, what is this I? Now I will be basically EMF by R. EMF by R. And EMF is what? BLV. BLV by R. So now you can find your I. So what is your I? Now I equal to BLV by R. I is BLV by R. So you can keep in box. Okay. So this is the amount of current that you can tell, basically induced current. Induced current in the circuit. Induced current in the circuit. See this resistance you can take small r also, but here I have taken capital R and I will mention also here. So capital R is basically resistance of the, resistance of coil, resistance of circuit. So that is the induced current flowing in the circuit. Now sometimes here they can ask, you just choose which is positive terminal, which is negative terminal. Suppose here you can tell Q is positive terminal in this particular case, and here P is negative terminal. And what is the direction of current? Now here direction of current is what? The direction of current is from P to Q in the circuit, here P to Q, but outside the circuit it is towards Q to P, like that, QRP, like that you can say. Okay, so whatever you want you can do there. Now next thing is basically what is the force. So what is the force on conductor? That one we will try to see. Force on conductor. So why force on conductor is coming? Now because we know when a conductor is moving in a magnetic field, it will experience a force, magnetic force. That is basically ILB. Already we know this. So that means the magnetic force on conductor is basically ILB. Okay. Now here I already you know what is I. Now BLV by resistance R into length L into magnetic field B. Now if you multiply this, so what you are getting? You are getting B square L square V divided by resistance R. So this is your magnetic force. Now if I can find now what is the force acting on the conductor. If this conductor is moving in the magnetic field, uniform magnetic field, here cross magnetic field is there, right? Yes. So here cross magnetic field is there. So in this cross magnetic field, my conductor is behaving like cell, and its force acting, magnetic force acting on this is B square L square V by R. Okay, resistance. R is the resistance, remember. Now next write. So force on conductor you understood. Now next write power in the circuit. What is power in the circuit? Okay. So basically you can tell power you write. So in power I will make you to understand. There are two powers are there. So P. So power is basically nothing but it is force into velocity. It is basically mechanical power. Whatever you are finding here, mechanical power. So force is basically B square L square V divided by resistance R, and speed V you can put here. So it will come B square L square V square by R. So whatever you are getting this one, so I will give this name. This is what? Now this is your mechanical power. This is your mechanical power. Why mechanical power? Now because when you are moving this conductor, in the uniform magnetic field, try to understand, you have to do some work, because this conductor automatically cannot move. Suppose this is the conductor, then my hand can move this. Yes or no? So that means here to move my conductor, whatever energy I required, that energy per unit time, basically power. So power is coming basically B square L square V square by R. This is the external things you are doing, external power. Okay. But now listen, if this power is coming, that is external work you did, where that work went? That work went inside the circuit, because in the circuit current is flowing and one resistance is there. So current square into resistance, I square R, will give you what? Now will give you power loss in the circuit. So heating effect happening. That means when you are moving the conductor, your mechanical energy getting converted to electrical energy. You are getting current, induced current. That induced current, that electrical energy, again in the resistor is there. In the resistor some heating effect will produce according to Joule's heating effect. So here heat is producing, right? So that means what is happening? Electrical energy becoming again heat energy. So that is what we told in this, starting we told no conservation of energy term. So energy is getting converted to one form to another form. Okay, just simply by moving things you cannot get current. It is not like that a gift of energy you are getting. You are doing mechanical work, due to that one you are getting electrical work. That electrical work again getting to thermal energy, like that you can tell. So now here I will write, this is the mechanical work. Now your Joule heating effect or Pj I will write. Okay, so that is your basically I square R. I square R. You will see also I square small r not give, capital R give. Now I square is basically I is B square L square V square by R square because I is BLV by R, and here one R will be there. Now if you will cancel here, you will get same thing, B square L square V square by R. You see, whatever I told in theory, now same thing is coming in numerical also. So this is your power loss in the circuit, power loss in circuit. Okay. So the both are same, mechanical power, this power is same. That means what happened? Now whatever mechanical work you did, it converted to electrical work, or mechanical energy got converted to electrical energy. So that is the energy consideration in this electromagnetic induction. Okay. So try to understand again. So magnetic force you got, after finding magnetic force you got mechanical power, that is your basically what? Now F into V, and after that you got what is your power loss in the circuit. Power loss in the circuit is B square L square V square by R, which is equivalent to your mechanical power. Okay. So I hope you understand up to this. Okay. So if a conductor is moving, in a uniform magnetic field, then it is behaving like a cell, and if it is behaving like a cell, its EMF is nothing but it is BLV. This EMF is nothing but how much coming it is? BLV, and if a circuit is connected, then its resistance is R, means your current is BLV by R. Then after you are finding the force, and now you are finding also power. Okay. I hope this topic is clear. Now next thing I want to show you some questions based on this, and if you are not translating the conductor, actually here particularly you are translating the conductor, suppose you are not translating, you are rotating the conductor, any EMF will produce or not in magnetic field, that one also will try to see. Let us go to the next thing. Okay. So before that there is some alternate method also given. This is for what you know, this is for derivation, this is what given. Now this is for derivation of BLV, alternative method, derivation BLV. So E equal to BLV, the derivation is given here. Okay. Okay. So in this derivation what they are telling actually, now consider an arbitrary charge Q in a conductor PQ. Suppose a conductor is there, so this is your P, this is your Q. Now any arbitrary charge, positive charge you consider. Now it is moving in a uniform magnetic field, so magnetic field is cross, it is moving in a uniform magnetic field B with speed V. Now this charge will experience a magnetic force. So this charge will experience a magnetic force downward, magnetic force it will experience. Now this all charge will come and accumulate here. So this charge is basically positive charge. Okay, this charge is positive charge, it will accumulate where? It will accumulate here, the down in the Q, they will accumulate all positive, they will accumulate. Okay. Now here, that is what they are telling, a Lorentz force will act, a magnetic force Fm, that is QVB. So here what is this Fm? This Fm is nothing but it is QVB acting on this charge. So whatever charge at P, also positive charge, they will move and come to Q. So the length distance L, they will travel and they will come. That is what the alternative method is telling. Now the work done in moving the charge, that small charge Q, small q, from P to Q, how much it is? Now this work done from P to Q will be force, magnetic force into length. And what is magnetic force? Now that is QVB. So it is QVB into length L. So this is your work done. Now from here if you want to find the EMF, this EMF we want to find, right? You want to find that EMF. So what you can do? Now EMF is basically work done per unit charge, because it is a potential you know, basically energy by charge, energy per unit charge. Now here your EMF will be, you can write this one, whatever work you got, QVBL, so write here QVBL divided by Q. Now this Q getting cancelled, now you are getting same thing, check BLV, so EMF is coming BLV. So this is also a short method to derive E equal to BLV. Okay. So E equal to BLV, that one you can derive also in this method, E equal to BLV. I hope you understand. Okay. So now next thing come. This is extra thing, keep in mind. Now question. Here they are telling a metallic rod R, a radius R meter, okay, or length basically, length is R meter. Now with the frequency omega radian per second, with the one end hinged at the center and other end at the circumference of a circular metallic ring, about an axis passing through the center. So they are talking about what you know, one rod is there, this rod is attached here like this, okay, this radius is R or length is R, okay. Now what doing this, now this one is moving with angular velocity omega, moving with angular velocity omega, okay. Now next, it is moving in a circumference and it is in a uniform magnetic field like this one, circumference of radius R, okay, of a circle. Now here uniform magnetic field is there, everywhere uniform magnetic field is there. If you do like this, an EMF will produce in this conductor, yes, induced EMF will produce here. And what will be that induced EMF formula? That will be different than BLV, that one we will try to understand now, okay. So that is what picture is given here. A conductor is rotating like this, a conductor is rotating like this in a uniform magnetic field B, radius is R. Now what is your induced EMF here? That is called basically rotational EMF, you can tell, okay. So if rotation happening, their EMF is inducing. So that one we will see. So you can write down the question along with picture. So here omega, and it is moving with this movement is basically V, you can tell, and this V is basically omega into R if total radius I will consider. Each and every point you can check here with move with certain velocity V, depends on what point you are taking, okay. And the length of the rod is R, and center is O, center of the circle O you can give. Now next see. So what is the answer? You can write this language little. After that, what you consider, now here I will do here, you consider this is a conductor actually, so this is like conductor I am doing. You consider a small element here in the conductor. So this is the center O, and it is moving in the circle, already we know this one, it is moving in the circle. Now consider small length dr, from here to here distance is R, this dr is moving with V, here angular velocity is omega, this V equal to nothing but omega into small r. Small element you consider dr, okay. Now what due to this small dr, what is the EMF? Now dE, that is BV dr, because already magnetic field is there, already cross magnetic field is there, okay. So here what coming? Now D is coming BV dr, because you know EMF equal to BLV. So here small element, that length is like a D, L is like a dr. So small EMF is moving with uniform magnetic field V means it is BLV or BV dr, you can tell. Now here I can write DE, B, this V is nothing but omega into R dr. Now here it is DE, now B and omega they are constant, let us take out, and R dr you keep separately. Now you do the integration. What integration? Now here small r it is 0 and here small r equal to capital R. So 0 to R you do the integration, now you will get the EMF. So DMF integration is E, EMF, total EMF B omega. Now here it is R square by 2, 0 to R, R square by 2, 0 to R. So lower limit is 0 and upper limit is what? Lower limit is 0, upper limit is capital R, okay, because small r value changes from 0 to capital R. Now if you substitute this upper limit, you will get B omega, this R will be there here, R square by 2 will come, and minus 0 square by 2, no need to include. So now this is the thing. Now if you write this one correctly, you will get half B omega R square. So what you understood, if a conductor is rotating in uniform magnetic field, okay, if a conductor is rotating in uniform magnetic field in a circular path of radius R and conductor length also R, then EMF induced in the conductor is basically B omega R square by 2. So that means this will act like again a cell, and it will also have EMF, that EMF is given by this. And you can understand also same V cross B you do, you can understand where is positive terminal, where is negative terminal, okay. where is positive terminal, where is negative terminal, you can identify from B cross B, because V cross B will give you positive terminal. So once you get positive terminal, you can get the negative. So V cross B you have to calculate. The direction of V cross B will give you positive terminal of the cell. Okay, so we are towards the end of our lecture. So we understood what is the rotational EMF. So if a conductor is rotating, so if a conductor is there, it is rotating like this, then also you can find the EMF. So first we saw a running conductor. So this is a conductor, it is running, then it will behave like a cell. Its EMF is BLV. But again we saw if a conductor is there, now it is rotating. This conductor is rotating like this. Okay, one end is fixed, other end is rotating like this, then also it will behave like a cell, or it will have some EMF. That EMF is basically half V omega R square. Okay. So based on this, you can do one question from NCERT. So this is your NCERT example 6.6. So please you try this NCERT example 6.6 homework. You complete this, you check what is given there and find it out. Now let me do the next example, which I have taken in terms of MCQ. A wheel is there, 10 metallic spokes. So they are telling here, one wheel is there here, it has a 10 metallic spokes. Suppose like this one I am doing. Okay. So how much? 3, 3, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This one 10. So 10 spokes is there, one wheel is there. And each spoke has 0.5 meter long. So that means here length is given. Length is 0.5 meter. Each spoke here. Each spoke is having length 0.5 meter. Okay. Now this all spokes are moving like this. So with angular velocity is what? Omega. So omega is given. How much omega given? So let me write here directly. So omega is given 120 revolution per minute. So 120, 1 revolution is 2 pi radian, 1 minute is 60 second. So if I will convert this one, I will get 4 pi radian per second. 4 pi radian per second. So omega equal to 4 pi radian per second, that is given in question. In a plane normal to the horizontal component of Earth's magnetic field, Earth's magnetic field they are telling as HE. This is Earth magnetic field. So what is HE? HE is basically 0.4 Gauss. So here magnetic field I will write directly B, I will write 0.4 Gauss, or you can write 0.4 into 10 to the power minus 4 Tesla. Why? Now because there is a relation, 1 Gauss is 10 to the power minus 4 Tesla, and Gauss is CGS unit of magnetic field. So Gauss is not SI unit of magnetic field, it is CGS unit. That's why you have to convert to Tesla, because everything here meter is given, here radian per second is SI unit. Okay. So I must need to convert the all units. All are meter. Here it is radian per second, you see. Okay. So all data I got. B omega L. Now they are telling it is rotating actually. This all spokes are rotating. What is the induced EMF between the axle and the rim? So this is the rim actually. This is called rim and this is called axle. So between rim and axle, what is the EMF? So that means they are asking about the rotational EMF actually. Okay, they are asking about rotational EMF. So just now you understood what is the rotational EMF. The rotational EMF formula, this E equal to 1 by 2 B omega R square. But the R they did not give, they gave L here. So no need to worry. That R equal to L only. That radius equal to L only. So L square, half B omega L square. So you can ask here, sir, this induced EMF for one conductor you took this one as, one conductor we took basically this one. But in this question they are given 10 conductors. They are given 10 conductors. Should we multiply 10 here to find the total EMF? It's not like that. Because you see, all conductor, each and every point is connected to here. One end is connected to axle. Another ends are connected to rim. So that means this all cells are in parallel connection. Remember like this. All cells are in parallel connection like this. Okay. All cells are in parallel connection. And you know, if in parallel connection, if you want to find EMF, if each EMF is EEE, if you want to find total equivalent EMF, so what is equivalent EMF? Then same E. So no need to multiply 10 and all here. Just directly you find this. Because they told me 10 spokes are there. So this one no need to include, because this all are parallel connection. If cells are parallel connection means just only one you calculate. So now write EMF equal to half B. Magnetic field is given, so directly I can put here. No need to write any here. Now B is what? 0.4 into 10 to the power minus 4, and omega is already 4 pi, and L is basically is given already 0.5 meters, so I can write it as 1 by 2. No worries. 0.5 is 1 by 2. Square is there, so square let me write also. Square. B omega L square. Okay, now calculate here. So here if you will calculate, this 4 and this one will get cancelled. So let's check here, 1 by 4 and this one. 4 and 1 by 4, this will get cancelled. Here it will get 0.2 pi, 0.2 pi into 10 to the power minus 4, or you can write it as 2 pi into 10 to the power minus 5 volt. Okay. So 2 pi into 10 to the minus 5 volt. So but here pi value they have substituted here. So pi value is 3.14. If you multiply that, you will get 6.28 into 10 to the power minus 5 volt. So your EMF is coming how much? 6.28 into 10 to the power minus 5 volt. Why? Now remember, pi value is 3.14 and 2 pi means 6.28. Multiply. 3.14 into 2 means 6.28. Okay, so answer will be B here. Answer will be B. So I hope you understand. So here the concept to remember, B omega L square also you are doing, half of B omega L square. Omega is angular speed or angular frequency you can tell, but that unit you are converting correctly to radian per second, everything you are putting, and you are not multiplying 10 here, because if you 10 multiply means this will be answer, which is incorrect. This cannot be answer. Answer will be 6.2 to 10 to the minus 5 volt. So number of spokes does not matter here. Instead of 10 spokes, 100 spokes also giving here in this wheel, the number of spokes does not matter. That is what you have to remember, because this little mistake can give you wrong answer. Okay. So I hope you understand. We'll stop here. Note it down, and again you read and revise the concepts and questions. You'll get the idea better. Okay. Thank you all of you. Thanks for watching. All the very best. Likes and subscribe Vidhyalakshmi NEET Academy YouTube channel.